Ben şöyle kenara çekebiliyormuşum hocam, pardon. Son bir saniye. Şurada şöyle bir hareket yapabiliyorum.
Okay.
Tamamdır.
Okay, excellent. So, welcome to Feza Gürsey Institute Higher Structure Seminar. And today our speaker is Ödül Tetik from Zurich University. He is a very young mathematician, and his talk is, the title is quite complicated. Field theory from homology are duals, and field theory and homology via duals. So it is combination of these two titles. So welcome, Tetik, and we are listening to you. Yeah.
Thank you. Thank you for having me and for the invitation. I just realized I messed up the title. So it should be, the first title is Field Theory from Homology via Duals, or Field Theory and Homology are Duals. So I'll try to, so this is a very sloganic statement. I'll try to motivate it and essentially tell you what's known about this statement and what new I can tell you about it. So I will have a few parts in this talk. So the first is motivation. Then I will tell you known things about this. So this involves work that has been done essentially over the past 15 years, almost, a bit more. I mean, the origins of the techniques go way back, but these ideas have been developed in some degree of formality and some degree of precision over the past 15 years, one could say. Then I will tell you what's wrong. So there's an intermediate chapter, if you will, about what's wrong, or like what are the problems in known approaches. And finally, I'll only give you the essential ideas in a solution I will propose. Essential new ideas. There are some students outside the door, so I hope you don't hear them. So yeah, let me just start. I mean, okay, in this seminar, in many higher structure seminars these days, people talk a lot about field theory, so I won't go into details. That's one side of what I will talk about, and then I'll talk about connections to homology. Homology understood very broadly, and I will make that precise. So some major, like one major definition at least, I will make precise. For other ideas, I will give you pictures, and I mean, all of this will appear in written form soon, hopefully. So for details, I mean, we can talk about it, or you'll have to wait a little bit to see it in writing. So as for motivation, let me tell you a few problems with the functorial field theory as it stands today. So functorial field theory, I'll abbreviate to FFT. So this could be classical or quantum, so I'll just say functorial field theory. So I won't define it, but I'll just say a few unsatisfactory things about functorial field theory that you will notice from the start after T.S. definition. So like, so in codimension 1, so where you allow boundaries only, there's like the first definition that you will see is, okay, you have some functor to from Bordisms to vector spaces with linear maps. So Bordisms go to linear maps, the boundary components go to vector spaces. But if you want to extend this idea, like in the cobordism hypothesis, you want to allow corners of any codimension. Hopefully, there are many problems about the Bordism category and also the target categories that you can pick. And constructing such functorial field theories is it's a whole domain in itself, and there are certain problems. So I will just talk about a few that I mean, most of it I will try to address in the talk. So in functorial field theory, it's hard to do a few things. So first, it's hard to formulate it. if you want to allow any codimension. So this is it's hard to formulate beyond codimension 1. 2, it's hard to construct it. Or even if you allow yourself the cobordism hypothesis and you have some input datum of the appropriate sort, it's hard to still calculate what the functorial field theory does. As Lurie himself points out in his famous cobordism hypothesis paper, like the statement is very nice, but it's kind of useless because it's very impractical. You have your data at the level of points. Is completely impractical and impossible to calculate what the field theory does, even if it's in principle doing something in on higher dimensional Bordisms. And also in its current mathematical form, it's hard to interpret physically. So even if you construct something that looks like a functorial field theory, it's not clear what it means physically. So like, what is the thing at the point that's doing if it's fully extended? Is it an algebra of observables of some theory? What are the Bordisms going to in the target category? So what are they doing physically? It's not clear. And the data that you need is also not easy to interpret physically. So you need, imagine you have the cobordism hypothesis, so you know the statement says at a point you have to pick an object of a certain type in some category. So how are you going to find such an object? And what does it mean physically? It's not clear. This is like beyond the more elementary physical questions of, okay, if, codimension 1 Bordisms somehow model time evolution, what do higher codimension Bordisms model, physically speaking? So I'm not even talking about that. I'm just saying just the data even is not easy to interpret physically. So I will concentrate on 2 and 3 in this talk. But let me just say a few just words. I won't write it down to not spend too much time on it. But point number 1. So as I already said, formulation. So there are many technical issues with the definition even of the Bordism category. This is still half open, even though after Lurie's paper, there was a paper by Kalak and Scheinbauer on the definition of an infinity n category of Bordisms. It seems to be clean. Although I have not checked it myself, but we could trust them. Lurie says, of course, that his whole cobordism hypothesis paper is a sketch, and if you read it, you will see even some definitions are not precise. It's not clear what things mean exactly. And also there's a lot of required structure that you need to specify. So that's also hard as for point number 1. So in point number 2. As I already said, so the problem is even if you know what your fully extended theory does at a point, you won't in general be able to figure out what it does on higher dimensional things. That's very sad, because then what are you doing in the end if you cannot see it? And the datum that you need is hard to come by. So in low dimensions, as input, you could use a representation theory of like representation categories of quantum groups. So appropriate types of input. There are state sum functorial field theories that use different kinds of input. Sometimes these things coincide, sometimes they don't. And also they are hard to come by. Point number 3, you would ideally want to just start with the algebra of observables of some physical theory, like an actual observable algebra, and build a functorial field theory from it. If it's a local theory, and so you would ideally start with a disk algebra of some sort, which would just describe, okay, if I have a manifold on an open, I have this observable algebra, I can multiply them like in this manner, like as in a disk algebra, and you could say, well, okay, this is physically, the disk algebra structure is physically talking about correlation functions. So ideally, physical data should be enough to build this kind of assignment, like a functorial field theory. So okay. So I will concentrate on 2 and 3. I won't go into 1 at all. And I will talk about these combined. So ideally, the goal would be construction. So ideally, you would want construction from physical input, which is easy to formulate mathematically. So as I said, you would ideally want a functorial field theory given a disk algebra of the appropriate type. So I'll just call this physical input. And I won't discuss any physics. So if you're not comfortable with that, that's okay. So I'll just talk about disk algebras. There are many examples. Once you allow yourself to work with disk algebras, all sorts of physical theories, like essentially everything, every theory you can formulate as a disk algebra. Like you can extract the disk algebra out of it. So examples, like everything is an example. So, okay. The approach I'll talk about, so this is one goal. There are some other things we would like to do, so I'll get to them. So in the approach I'll talk about has its origins in Luri's paper already. So if you go to the last section, he will tell you that, okay, this is all very nice, but we can't really do anything with it. If only there was a way to construct a functorial field theory given an input algebra that we can actually manage. So this goes back to this goes back to a suggestion of Luri. So he talks about this not in terms of factorization homology directly, although he does. So it's not so clear. There he gives a sketch. I will say more about factorization homology in a moment. So this is the homology part of the title. And this was later taken up by Scheinbauer in her thesis. So Scheinbauer's thesis. So the Koborzin hypothesis paper of Luri is, I'm not sure, so maybe from 2008, 2009, not later, I don't think. Scheinbauer's thesis is from about 5 years after that. Okay. So the target, as in the target category of the functorial field theory, like a generalization of vector spaces and linear maps between them. So for the target category is a direct generalization of that. It's going to be a, let me say for the moment, representation category. So this is not the input like with quantum groups, but this is the target. This is a representation category. So it's going to consist of algebras of a specified type, by modules or bimodules, and so on. Let me put ... with compatible actions. I will go into this in a more pictorial manner. So if you don't like algebra, don't worry. And input for the theory is just going to be a disk algebra. A disk algebra of some dimension. So this could be a little disks algebra or little cubes algebra that's allowed. So like from classical topology. Of some dimension. So if you remember that bit of classical topology about disk algebras, recognition principle, iterated loop spaces, that whole business. So algebraically speaking, in that context, the dimension of the disk algebra is specifying degree of commutativity. Okay. So as for the actual construction, so this I said, okay, it uses factorization homology in a specific way. And essentially it uses pure topology and geometry. It's nothing too fancy. And the drawback, physically speaking, of this kind of approach, you might be surprised because this is supposed to be like the physical approach, like the simplest approach to constructing functorial field theories. You just start with an algebra. The drawback is that there are no partition functions. So when you advertise functorial field theory to students, you will say, oh, you can attach numbers to manifolds, so you cannot do this in this approach. Or you have to do more to get to numbers assigned to manifolds. So no partition functions. So this is if you want without taking traces. So there are no numbers attached to manifolds in this approach, at least at the level that I'll talk about. More upshots of this approach before I start giving you something more concrete is if you want the philosophical point of this talk, which is duality between functorial field theory and homology, understood very broadly. So makes this duality that I will explain a bit more apparent. And a bit deeper understanding would lead, which is the topic of this talk, more concretely speaking, would lead to, well, if you already know this business, you will know what I mean now. So otherwise I will talk about this in a moment. You can do this now with any tangential structure, like beyond Lurie and Scheinbauer. And as an upshot, as a final upshot, I will mention a new-ish concept in elementary topology. Or geometry. Doesn't have quite a name yet, but we'll get to it. You'll see what I mean. So, okay. These are just some words. So known things. So the goal is, given disk algebra, A, let's say, so in some underlying category. So let's say, okay, disk algebra with some structure that I will get to of some dimension in some target, okay, this is not the target category that I talked about above, but let's say this is some target category where the observable algebra lives. So this can in general be a symmetric monoidal infinity category with some properties. The properties allow you to do factorization algebra with these coefficients. So this could be, as examples, this could be chain complexes with plus or times, so direct sum or a tensor product. This could be spectra with smash product or wet sum. Could be many things. So there are very mild assumptions on this category for the construction to work. So goal is, given a disk algebra, construct a functorial field theory, fully extended. So this means construct, let's say, f of a, even though I won't use this notation. Let's just to give it a name. Oops. So a functorial field theory is a functor from a Bordism category with some tangential structure, with some top dimension. This is going to be the same dimension as the dimension of the disk algebra. and to some target category that has to do with T. I'll just put question mark T. In fact, there is a major issue here. So there are two major issues here. This won't work. The same structure, so this is the tangential structure that I will get to in a moment, won't work, so you have to put a modification of this here. And also the second major issue is how to construct this category that has to do with T. And so known technology about disk algebras is this. So there's a major theorem about disk algebras that you should take away from this talk, which is actually not a hard theorem. So disk algebras with whatever this structure means that I'm calling B in dimension n with values in T or coefficients in T. So this is the same in a certain sense. There's an equivalence of these things between these things, and homology theories in a certain sense that go from manifolds that can evaluate manifolds with that B structure, with that tangential structure, valued in T. So what does this mean? So this is saying if you have a disk algebra, this is the local data, which is why in the functorial field theory side, you would think of this as the thing that you're assigning to a point. This is the local data. Here it's saying you can evaluate global things given a disk algebra. You can evaluate a manifold if it has the same kind of tangential structure as the disk algebra. You can also evaluate a manifold using just the disk algebra. So just the local data. So this is like a local to global. Okay, let me not call it that, but this is just it's saying there's a way to evaluate manifolds given just local data. And in fact, if this evaluation is local enough, then this is the only way to do it. And this assignment takes, so this equivalence takes a disk algebra and sends it to factorization homology with coefficients in that disk algebra. So here, under the integral sign, there's an argument. That's where the manifold goes. So this will be somebody in T. And once you put the manifold. So I mean, okay, let me not write it like that because then it's not correct. So this is something that goes from manifolds to T, where the manifold you put under the integral sign. So okay, let me say what functors like this are. So H here means, so curly H means functors H from manifolds to T, such that, well, this joint, so this is symmetric monoidal, this joint union goes to tensor product, so T has a tensor product. Like in the examples that I mentioned above. So this is monoidal. Then there is, okay, this is that. Then there is an excision property. So this is if you want the locality property of such functors that you want to impose. So this is a cutting gluing property. It's a very simple property to state. It says if you take a manifold M and it's glued along some hypersurface. So if you write M as M0 union, oops, that's a union. M0 union R times some hypersurface and M1. So this R factor is just a color along the hypersurface. It just extends it a little bit into M. You can think of this as an epsilon parameter. Then this functor evaluated at M is at least isomorphic in T to H of M0 tensored over H of the hypersurface with H of M1. It was just this is like a baby Maya Vittorius kind of situation. So it's just saying cutting and gluing H is local in this sense. And the last thing, which we won't even use, is there's one final condition. That's it. This is the whole list. There's a continuity property or exhaustion in classical terminology. So this would mean if you have, if you can write M as a sequential union. So imagine you have some M0, an open subset of M1, M2, etc. And all of these are open subsets of M, such that M is the union. Then H of M is the co-limit of the H of Mi's. So then you will have, I mean, these things are covariant, so the arrows go in the same way. So this is homology. So you have this situation. The co-limit of this diagram should be, well, should be HM. So this is it. If you have a functor that can evaluate manifolds with these three properties, I mean, one is just monoidality. The major property is excision. Then this is saying, well, any such functor is just factorization homology for some disk algebra as input. This is due to Ayala, Francis, and Tanaka in one of their factorization homology papers. Okay. Okay. So let me talk a little bit about what this suggests in terms of this duality between functorial field theory and homology. So such a thing.
Can I interrupt with a question about the nature of this result?
I couldn't quite hear.
Could I interrupt with a question about the nature of this result? Because it's like a representability result, right? It's like
yes,
a result of motivic flavor, actually. Does it take? I mean, I've read this paper, but not very carefully, and I don't remember. But so is it the kind of like generalized cohomology theory? You know how algebraic K theory is in some sense the universal cohomology theory, something like that. So is it comparable to something like that? Because these properties are quite analogous, especially.
yes, yeah. In fact, yes. Morally, yes. But the proof is not so hard. I mean, in a sense, these representability theorems are not so hard, but they are important. So like Brown representability also, you know, the techniques are not very deep, but so morally it's the same kind of result. But it's not, as far as I know, formulated in more generality. Yes. I mean, I didn't really answer your question, but it's a result in the same spirit. It doesn't use any, I don't think it uses any like standard arguments in representability theorems. So it's just
an isomorphism, I suppose. I mean,
yes, yeah.
Okay.
Yes. Yeah. So in a sense, it's yes. You could also see this as like another incarnation of the Yoneda dilemma.
Right.
Yeah. So in terms of this functorial field theory homology duality, you should read this. So this is a sloganic thing that I will just state and try to motivate a little bit. You should read this as the Coborzheim hypothesis, only on the homology side. So this is, so the right-hand side is this H, you should read as if it's like some sort of dual of functorial field theories. And the left-hand side, you should read as what you assign to a point. Only the dimensions are completely inverted because disk algebras are of full dimension, like n is the top dimension. And there is, so on the right-hand side with manifolds, you only have actually top dimensional things that you're evaluating. I'll get into this, but you should read this as a simple Coborzheim hypothesis statement if only you had a duality correspondence between functorial field theory and and homology. So, of course, here there's a problem. This is a relatively easy result, and it doesn't imply the cobordism hypothesis immediately, because the duality statement is the hard part. Then, I mean, by the conservation of difficulty, the duality is then at least as hard as the cobordism hypothesis. So before I go on, let me just say a few words just to give you an idea about this duality, where I'll just talk about the categorical structure first on the side of functorial field theory and then on the side of homology or factorization homology. So one could make a little table here to compare them. So on one side you have functorial field theories, on the other you have factorization homology. The compositions, so the notion of composition is different on the two sides. So let me just explain a little bit. So here things happen by gluing on functorial field theory. Here things happen by merging or collapsing. You will see pictures about this. So, or more descriptively, morphisms here are described by cutting. So instead of gluing, you're talking about cutting. We will see this in a moment. Okay. So gluing versus cutting is one aspect of this duality. So here, when you compose, this is just composition of maps. You know, like in a TSCL, you compose linear maps between vector spaces. Here, you take tensor products or monoidal products, whichever. And well, the interpretation is on the FFT side, time evolution of states. On the factorization homology side, this is what corresponds to this is gluing of observable algebras. So this would be like folk-like. So they are completely different but related. Okay, let me just talk a bit about the known case, and if there's time, I'll say a few new things. So the known case where this correspondence has been worked out is a special case. So if you remember, we have this B that we've been carrying around. So there's a specific B for which this has been worked out. So following Luri's suggestion and essentially in Schamberger's thesis, to a good degree of precision. So known case is the simplest case if you want. Known case is B is just a point. What does this mean? So let me tell you very briefly about tangential structures, just to recall. This means you're only talking about framed things. So this is the easiest kind of tangential structure. It just means everything tangential is trivial. There's no tangential information. So a tangential structure, generally speaking, is, so in classical topology, is some space that maps to BO n, let's say, or you could just have it map to any of the BONs you want. So normally B could be, classical examples would be B SO, and B spin and etc. So a B structure on M, a manifold, is just a reduction of structure group. So imagine you have an n-dimensional manifold, its tangent bundle is classified by some map to BON, and you have this space that's mapping to BON that is given. A lift together with somebody that commutes this, a homotopy that commutes this diagram is a B structure on M. So if B is just a point, this corresponds to framings. If B is just a point, this composition is constant because it factors through a point. This is saying there's a homotopy between TM and the constant map from M to BON, which is the framing. So this homotopy would give this bundle isomorphism. So this trivial bundle Rn over M is classified by this constant map from M to BON. That is the composition. Okay. So in this case, so B is just a point. So we're talking about framings. Then the way to get a functorial field theory from a framed disk algebra is, so how does this work? Is you take, so you're only allowed to, because you only have a disk algebra, let me just go back for a moment. Because you only have a disk algebra, you're allowed only to evaluate framed manifolds with your disk algebra by factorization homology. This actually means, so the framing, so B being just a point is not all the information. The point is mapping to one of the BONs. So the N is fixed. This means all these manifolds that you're allowed to evaluate are fully n-dimensional. So they cannot be like boundary components of Bordisms. They cannot be lower dimensional than N. And they have to have on-the-nose framing. So you have to take a framed colors of your Bordisms. So you have to complete your Bordisms to actually frame things of full dimension. And use factorization homology in a certain way. And there's another thing that you need. Which is a theorem due to Lurie. That, I mean, there are two more things that you need. One is a theorem due to Lurie, which is to say that EN algebras or framed n-dimensional disk algebras, so they are the same as EN algebras, with whatever notion, like whatever particular convention you picked for EN. So framed n-dimensional disk algebras are the same. So let me just state it a bit imprecisely. So this is disk algebras framed n-dimensional in T. So this is the same thing as locally constant factorization algebras on Rn. Plus you need the Dan-Lurie additivity. So these are specific facts about the N algebras. So Dan-Lurie additivity says En plus M algebras are the same as En algebras in Em algebras. So this means En plus M is En in Em. So these are specific facts about the En algebras that are known. And then you can land in, so you can construct a functorial field theory. And what is the target category? So this representation category of algebras, modules, etc. that I mentioned. This would be so this is the modification of T that I denoted by question mark T that you need as the target of your functorial field theory. This would be the so-called Movita category of En algebras. So let me put a few qualifications around Morita with coefficients in T. So what is this category? So what do like k-dimensional Bordisms go to? And so here, objects, so in dimension 0, so these are just EN algebras. One morphisms would be, let me just write it a bit suggestively. An one morphism is an EN minus 1 algebra, and it has to know about the source and target, which would be objects. So they have to be, so it comes with the source and target. So there's an EN algebra and another EN algebra, and these two act on this EN minus 1 algebra. So this is a bimodule. And these actions commute in a certain coherent sense. And N morphisms, so this is the top dimension. So this is what top dimensional Bordisms go to. These would be, so E0 algebras, which are just pointed objects in T. And then there will be, it will have some actions, and these things will receive actions. I mean, there are some things here that act, etc., etc. There's a whole system of actions. This is hard to define algebraically. This has been done. There's a treatment, algebraic treatment of these things by Hao Sang. But this is, we won't need this. I'll give you pictures for this. I mean, you don't have to memorize this. The pictures follow right now. So, okay, visually, so in dimension 2, let's say. So what does such a system look like? So in dimension 2, you would want a two-dimensional disk algebra. So this could be just a commutative algebra in some category as input. And you want to evaluate Bordisms of dimension up to 2. So if you have something closed, top dimension, this has to go to some E0 algebra. And I will draw pictures in terms of this theorem that I mentioned. So in terms of some RNs. So this, the underlying space, this would go to a point. Oh, let me just draw a point. So a locally constant factorization algebra on the point is just an E0 algebra. So that's a pointed object. So I'm interested for this talk in just the correspondence between these spaces, essentially. If you have a, how shall I draw this? A two-dimensional thing with one boundary component. Okay, maybe let me not draw the color. Okay, so it can have whatever topology. So note that, so this is what I will call the dual. I will introduce this more formally if there's time, I hope. Note that this is not a duality at all in the usual sense. So any closed two manifold goes to the same space here. It just goes to the point. So it doesn't remember. This is not a reversible process. It's not a bijection. So such a thing will go to a locally constant factorization algebra on a space like this. So here, this point is coming from the interior. So you just take out the boundary component if you want. So this is just the interior, and it's full dimension, no boundary. It's just going to a point, and the boundary itself is going to a half line, or this half line without the point. So it's just going to a line. This is the boundary. This is coming from the boundary. You could, in fact, do something like this. If you only have a one-dimensional thing, this you can send this to a locally constant factorization algebra on just R. So here, this would be an E1 algebra. Here at the point, you will have an E0 algebra living. On the line to the left, you will have an E1 algebra living. and saying that these coupled to a factorization algebra on this stratified space, this half line, will mean that there is an action of this E1 algebra on this E0 algebra. I mean, this E0 algebra is just a pointed object. And so similarly, if you have two boundary components, this will go to locally constant factorization algebra on a space of this type. So here, so this is like the boundary to the left, the boundary to the right. This is the interior. We'll have an E0, E1, and there will be an action like this and an action like this, and they will commute in a certain sense. So this would be in the Morita category an N morphism, a 2 morphism, if you remember this list. So there will be intermediate things like this. So this is how the category is built. So instead of an algebraic treatment, you could just talk about locally constant factorization algebras on simple stratified spaces. Okay. I will skip how these actions actually work because there won't be any time. And a deeper question would be, why these spaces exactly? Where do these spaces come from? That's the main question I will try to address. So I have about like 10, maybe we started a bit late, so 10 to 15 minutes at most. I will try to give you some new ideas and try to tell you how you should understand this procedure more generally. Because all of this is framed, but you can understand these spaces more generally, these spaces on the right that come out, and that would actually lead you to a construction that can deal with any tangential structure. But more interesting to me was to understand why these spaces exactly come up here. So just a few essential new ideas about this construction. So this construction can deal with actually physical theories. Only everything has to be framed. So it's very inflexible. You know, if you're a three-dimensional, I mean, many interesting manifolds are not framed. So, you know, like you cannot talk about S2 in a 2 or 3-dimensional theory. So it's not great. Okay, first thing, I'll do what I can with the time. So first thing I should tell you is you should look at Bordisms not in the classical context, but as stratified spaces themselves. So this means you should treat the interiors and the boundary components and the corners, etc., as separate spaces that are glued together into a stratified space. So two, you should derive polar and dual as in the space that you get here on the right-hand side, these simple spaces, directly from stratified geometry, which is possible. Well, third, let me just say, use factorization homology appropriately in this context. So so the general theory of factorization homology can handle stratified spaces, and that's enough to do this construction. So okay, let me just say a few things. So what does this mean exactly? Look at Bordisms as stratified spaces. I won't go into details because hopefully in the next few days. So this whole theory is a very specifically, I mean, conically smooth stratified spaces. The idea is a very old idea. The idea of a stratified space goes back to Whitney at least. so there's a recent theory of conically smooth stratified spaces that is particularly useful. But I won't go into details because hopefully in the next 2 days there will a paper will come out that treats that gives a treatment of this without using any stratifications, but like systems of unstratified objects. So I won't say too much about this. I will just say about tangential structures in a few words about tangential structures in stratified geometry. So there is so Ayala, Francis, and Rosenblum introduced they don't call it this, but they introduced the stratified Grassmannian. Which is a replacement of the BOs. Namely, so all the BOs become well, there's a new space in a certain sense of the word. So V is for vector space. And this hook arrow is for injections. So this is so BON is replaced by a category of vector spaces together with injections. So this should be treated as an infinity category. Well, on this side, you had an infinity groupoid. You can take the singular chains of this thing, you would have an infinity groupoid. So all the paths and everything is invertible. Here, injections are not necessarily invertible. So this is only an infinity category. But essentially this, so on the left-hand side, the BONs you can think of as just vector spaces with isomorphisms. Vector spaces of any dimension with isomorphisms. Here you relax this to injections. This is about lower dimensional strata like boundary components sitting inside higher dimensional strata. Or being glued to higher dimensional strata, that's why the injections come up. And stratified tangential structure has a similar definition. It's just, well, in this case, instead of the BOs, you talk about the stratified Grassmannian, which is an infinity category. So you just say, okay, instead of a space sitting on top of BONs, I want an infinity category sitting on top of the stratified version of this Grassmannian. So this classical tangential structures are all examples. So this doesn't lose any classical theory. This is just a generalization of the classical theory. And so in the classical case, we had tangential structures that were defined by lifts of this type. So you had some B, sorry, let me just like this, some space sitting on top of this, and some lift here, and some homotopy commuting this. So this becomes a similar diagram in the definition of a tangential structure on some stratified space, if M was stratified now. So here, this is the stratified version of the singular chains of M. So here, this is called the exit path infinity category. So this is an infinity category. Morally, well, the singular chains consist of paths, higher dimensional paths, etc., and everybody is invertible. So here, this is the version of it where paths from lower dimensional strata into higher dimensional strata are not invertible. So you can, as a path, you can go from a lower dimensional thing into a higher dimensional thing, but not the other way around. Okay. I'll just say that, okay. I'll just give you a special case of the general definition of a dual, and I'll leave you with that because I don't have time for anything else. So framed case, let me just stick to the framed case again, but you will see that it doesn't really depend on this. So the point sitting on top of the stratified Grassmann in this time can just be given by the point sitting on top of BOM. So here, so the singleton sitting on top of, and the unique point will go to Rn. It's a vector space. The issue is, if you remember, I told you there is a problem with the choice of this tangential structure when you say what the functorial field theory is supposed to be. So I had this kind of expression, like what modification of T, what modification of B do you need? Here, there are two possible choices. One is a bit more general. So this is the original B. So what is the modification that I need here? Because the power of the stratified geometry approach to this is just you can actually define this whole thing very easily. You can just say, I replace this. So this B. So everything is happening in infinity category language now. There are all sorts of replacements for maps of infinity categories. For Bordisms, two are advisable. So one is the thing used by Lurie and Scheinbauer, although not in this language. This is the easier version. So a solid, so these are replacements for this B. So this would be, so the solid version is easy to say because it's just a slice of this map from B to the stratified Grassmann. So in this particular case, the slice, so the over category, the slice looks like this. If I could have 5 more minutes, is that okay? Thank you, because we started a few minutes late. I'm almost done with this definition. The slice just looks like this. So, and the map, so this is a new tangential structure that you can define, given any tangential structure. I'm just telling you this is the correct replacement of the tangential structure for Bordisms. You can just take the solid, so there's a more categorical expression of what kind of replacement this is, but let's just call it the solid replacement. So this here means, before I tell you what stable means, geometrically speaking, if you have your space M, so Bordism M, this just means the tangent bundle embeds into some trivial bundle of rank n. This is all this means, at least in the unstratified case. Stable replacement is solid and the normal bundle of this embedding is trivial. This means, so in the solid case, this just means there is a Tm, so you could say T of M R to the codimension of M, which is just n minus the dimension of M, so n is the top dimension, is trivial. This is all that means. Oh, sorry. So this is the stable case. So solid plus this triviality of the normal bundle. And if you want, this is the dual of M in that kind of situation. And you can also define the dual quite more generally. And let me end with that definition. So imagine, so keep this in mind, because this is the definition that works for any tangential structure. So this is the case for the solid replacement of framings. So this thing that I wrote down here, but this works for any tangential structure. And so imagine you have your boardism. I'll just use this notation, but don't worry about it. Just concentrate on M. Imagine you have this boardism with its, so seen as a stratified space, just stratified by its boundary components, corners, etc., together with its tangent bundle. And imagine you do have a solid framing of it, solid N framing. So there is such a thing, and there's a lift and there's a homotopy, and let's call this lift T, small t. And let me fix one more notation. I'll just call N the opposite of, if you know this, you know what I mean, the opposite of the of this stratified version of singular chains. This is called the enter path category. Doesn't matter too much. I'll just have to take opposites at some point. So there is an induced map. So T, if you take its opposite, it goes to, okay, whatever its target was, but its opposite. Well, this thing is equivalent again to the original slice by taking orthogonal complements. So here, by taking orthogonal complements. Here I'm implicitly fixing inner product on Rn. This is the only extra data that you need. So it's a bit mild, but I mean, it's there. By taking orthogonal complements, you can, I mean, these are just, you should just think of this category as sub-vector spaces of Rn. These are just vector spaces that are mapping injectively into Rn. If you take orthogonal complements, op goes to double op. This is an isomorphism, orthogonal complements. Arrows go the other way. Injection, if you have an injection, take orthogonal complement, the arrow goes the other way. So you have this other induced map, therefore, into the same B. So this was the solid replacement for B in the case of N framings. I'll just leave you with this. So let's call this the dual. At least it's homotopy type. So this will be a stratified space whose exit path category, this is how you should read this, is just the image. Let's call this composition C for composition, just the image of C. So this is a full subcategory of, oh, it's not actually full, sorry. This is just some sub-infinity category of the solid replacement. Well, this guy comes with its own forgetful map to the stratified Grassmannian, which you should interpret as the tangent bundle map of the dual. The functorial field theory, this is the last thing I'll say. The functorial field theory evaluates from a color that I have no time to define. It pushes forward the disk algebra or the factorization algebra that the disk algebra induces from the color to this dual. I'll just give you this definition. I don't have time to go through examples. If you look at it in like a few examples, you will see that you recover as this dual all these spaces that we discussed here. Sorry for scrolling so much, but like these simple stratified spaces. The orthogonal complement taking that we did in this definition. So this is a very simple operation that we did. It's all about this taking, this orthogonal complement taking. Funny expression, but this is the crucial part of this. And geometrically speaking, it's all about this. It's all about this space that you're adding to your manifold by factoring by just taking Cartesian product, on which you will have an on-the-nose B structure, which in this case was just n framings. In general, if M has boundary components, etc., it won't be a Euclidean space. So here it's just a Euclidean space. It will be a Euclidean space with some flag-like stratification. So it will have like hypersurfaces. It will have some hypersurface in it, and the hypersurface itself will have some lower dimensional surfaces in it. But everything just planes, hyperplanes, I should say, not hypersurface, just planes. So just like pictures that we had here. Final thing, if you do stable, those are the spaces that you'll get. So in this replacement, if you do stable, those are the spaces that you'll get. If you do solid, you will get more than just Euclidean spaces, but you can still do this. The general construction of this space, so I just gave you its homotopy type with this tangent bundle, is open, but let me leave you with a funny example. If n is 3, and you take the open Möbius strip, so two-dimensional manifold, it has a solid 3 framing, but not a stable 3 framing, because it's not orientable. So stable 3 framing on the Möbius strip would imply orientability. Its dual you can compute, it's going to be a circle. It won't be a Euclidean space. If codimension is 1, in the stable case, you would always get some R, maybe with a point in it. In the solid case, for instance, with the Möbius strip, you will get a circle. This would have some physical interpretation, which I have no time to get into. But thank you for listening.
Thank you very much, Ödül.
Let me end the screen sharing.
Yeah. So any questions or comments? So in your last part of your talk, you talked about this, how was it called? Those solid replacement and stable replacement. Are they related to Scholz's condensed mathematic, do you think?
Oh, because of the terminology.
Yeah.
I don't think so.
Because
No. So the solid replacement is the categorically more natural thing to do. So it's basically a free vibration replacement type.
Is the solid replacement a vibrant replacement of some sort, or?
Yes. Yeah, exactly.
I see. Okay, so it is just a coincidental terminology.
Yeah. I mean, Ayala, Francis, and Rosenblum call it solid. They discuss this construction.
I see.
Not for this purpose, but they discuss this construction.
Oh.
There is a more categorical interpretation of it, so you can get it more universal. It has nothing to do with Schultz, unfortunately.
Thank you. Any more questions or comments? So maybe I will make one announcement. Actually, at 7 o'clock, there will be another seminar. It is a seminar of Turkish Mathematical Society, and the speaker is Professor Chudnovsky from Princeton University. So I will send links. So if you are interested, you can just join and listen to that seminar talk also. As you all know, she's a world expert in, I think, combinatorics, as far as I know. And I think Ödül, once more, actually, I think you are still a graduate student, right?
Yes. I
And
have one more year as a PhD, a bit more than 1 more year.
1 more year to go. I see.
Yep.
Very good. Very, very good. Yeah. So, and one more thing, our next next talk will be in after New Year. We have, it is, I think, on, well, I will send the details, but it will be the talk of Neslihan Gügümcü from İzmir Technology. She will talk on quantum notoids. I don't know what they are, but I mean, so that may be very interesting talk also. So I thank you again. So hope to see you in our next seminar talk. By the way, maybe I sent in the chat the details of Chudnovsky's link. So wait a second.
Thank you. Have a good day.
So I am attaching to the chat the link. Yeah. So this blue one is the link to. So there are some Turkish words, but what it means is that Maria Chudnovsky's induced subgraphs and tree decomposition seminar link. So it is like that. Okay, so see you all later. Bye-bye. I'm ending now. İlker görüşürüz. Bye bye.
Görüşürüz hocam. Sağ olun. Güle.
Teşekkürler hocam tekrar. Görüşmek üzere.
Görüşürüz. Hoşça kalın. Bye bye.